Hello students, here we'll go the basic introduction to logic gates and Boolean algebra. We are familiar what is analog, what is digital. In digital there are only two states. So here we'll go at the beginning the concept of logic gates. A logic gate is a building block having digital circuit. Most of the logic gates have two inputs and one outputs, and they are working on the operation is based on Boolean algebra. What is the concept of truth table? The truth table is used to represent the Boolean expressions of a logic gate functions. Depending on the input signals, the output is varies or gives the result. What is the function of logic gates? The logic gate performs the basic logical functions and the fundamental building blocks of digital integrated circuits. Here we'll proceed the basic logic gates and their category or the separations. So basically logic gates are categorized in the forms basic logic gates, universal logic gates and other logic gates. The basic logic gates are again further categorized as AND gate, NOT gate and OR gate, while the universal gates are NAND gate, NOR gate, and the remaining gates are XOR gate and XNOR gates. Now we will go in detail for all the types of gates. First, here we will observe AND gate. What is AND gate? It having two inputs or more than two inputs, and the output denoted as O is given by the formula O is equal to A into B. As there are two inputs, we say the combinations will be 4. Rather, A is 0, B is 0, A is 1, B is 0, A is 0, B is 1, and both may be 1, 1. So depending, these are the two inputs and our output y 0 is equal to A into B. Therefore, the multiplications we want to take as we are observing here the truth table. If both inputs are 0, 0, the output will be 0. If A is 0, B is 1, the output is again 0. If A is 1, B is 0, the output is again 0. And if both inputs are 1, 1, then and only then the output is 1. Here we saw the IC details for the AND gate. These IC details for the AND gates are nothing but IC number 7408, which having 1, 2 is the input, 3 is the output. For gate 2, 4, 5 is the input, 6 is the output. For gate 3, 9, 10 are the inputs and 8 is the output. And for gate 4, 12, 13 are the input and 11 is the output. Along with pin number 7, pin number 14 are ground and VCC respectively. Now we'll go for the next gate, that is OR gate. The OR gate functions that if A and B are the input, then output O is indicated by A plus B, that is the summation of the input signal. Again we are considering two inputs, so again there will be 4 combinations for this input signal. This is the truth table for the OR gate. Here again the IC we are observing that IC for OR gate is 7432 number, which having again 4 gates inside to that, and that's why it is again called as quad OR gate IC having number 7432. We'll proceed the next IC, that is NOT gate. Here the NOT gate is a digital logic gate which having one input and one output. We are also call this gate as an inverter gate. That means if the input is a single number, that is 0, the output will be 1, or if the input number is 1, then the output will be 0. This is the symbol for NOT gate. Just we are observing a bubble at the output that indicates the inversion or the complement of the input number. Here the IC for NOT gate used is 7404, which having one input and one output. Observe here, pin number 1 is the input, pin 2 is the output. Similarly, 3 is the input, 4 is the output, 5 is the input and 6 is the output. Here the total gates present are 6 gates, so it is again called as a hex inverter NOT gate IC having number 7404. We are observing the next gate, that is NAND gate. In NAND gate, these are called as the universal gates because with the help of NAND gate, we can build any other gates, that is AND gate, OR gate or NOT gate. Here the function for NAND gate is represented by output O is equal to A into B complement of the number. Means if input A and B are present, then the output will be the multiplications of the numbers and then we have to convert in the form of a complement. Let us consider if A, B both terminals are 0, 0, then their multiplication is 0. But for a NOT gate, we want to make the complement. So the output will be complement of 0 is 1. So the truth table we are writing in that way. And here only the conditions are verified as if both the inputs are 1, 1, then their multiplication is 0, 1. But because of complement, the output will be 0. So this is the truth table for NAND gate. And the IC here which we are observing again having 4 gates inside to that IC. The IC number for NAND gate is 7400. The bubble indicates the inversion of the IC. Now the next gate is NOR gate. NOR gate is a digital logic circuit which having 2 or more inputs and only one outputs. And the output equation for the same is given that A plus B complement of the number, where A and B both are the inputs of that particular IC. So if again two inputs are there, so the truth table again having 4 combinations. Either both numbers may be 0, 0, one may be 0, other may be 1, or both numbers may be 1, 1. So the truth table is nothing but it is exactly opposite to OR gate. Now if we are saying the inputs are 0, 0, then the output will be 0 plus 0 is equal to 0, but we want to make the complement of the number, so the answer becomes 1, which we are showing in truth table. Now below that there is a detail of the IC details. So this IC for NOR gate is 7402, which are again having 4 gates. But see here pin number 2, 3 is the input, 1 is the output, 5, 6 is the input and 4 is the output here. Along with pin number 7 and pin number 14 which are ground and VCC respectively. Now we'll proceed for the XOR gate. XOR gate output is coming as A XOR B, that is nothing but A bar B plus B bar A. Again we want to make the multiplications of the input numbers and we want to make the complement of the same numbers. So here this is the truth table, and for XOR gate if both the inputs are same, then at that time the outputs is 0. If the inputs of these XOR gates are different, then the outputs are 1. So this is the truth table for XOR gate along with the IC details. Now this is XNOR gate. The truth table is the output of the truth table is exactly opposite of the XOR gate. Now further we'll proceed for the total combinations of the gate what we learned here. So this is the tabular representations along with your gate name, the symbol for that gate, the function for the gate, that is nothing but the output equations, and the truth table for the gate. Similarly, here the diagram represents all IC numbers with their pin details. What we learned in the previous one by one, the combined group photo is here. Here the symbol for universal gates and the names of the ICs. We are going to say the NAND gate and the NOR gates are the universal ICs. Here the symbols are there. Using these two gates we can build the remaining gates. So here the diagram indicates the NAND gate is used to build the rest of the gates. That's why it is called as a universal gates. If the diagram indicates the symbol of NAND gate and the remaining gates prepared with the help of NAND gate, that is AND gate, OR gate, NOR gate, the XOR gate and the XNOR gate. Similarly, we are building using NOR gate the remaining gates. as OR gate, AND gate, NAND gate, the XOR gate and XNOR gate. And that's why we are going to say NOR gate and NAND gate as the universal gates. We'll proceed for Boolean expressions. Here the concept of Boolean logic is there. It is nothing but the electronic circuit that makes with the computers, and it is used on the basis of your binary logics, that is number 0 and 1, and basically they are used in different applications such as your personal computers, pocket calculators, CD players, cellular telephones, and so many electronic products. But using these Boolean expressions, they have to follow some steps for its simplifications, which are nothing but at the beginning, remove the parenthesis by multiplying the factors. Use exponent rules to remove the parenthesis in terms with exponents. Combine the terms by adding the coefficient and combine the constants. So here the properties of Boolean algebra is there. The properties are expressed in the form of and OR. AND is nothing but the multiplication word and OR is nothing but the addition word. So the properties here for Boolean algebras are commutative, associative, distributive, identity, complement, and De Morgan's law. Here the combined formulas are presented. We are saying the x is the variable here. You may assume any other variable. If we are saying x plus 0, the answer is x. X plus 1, the answer is 1. In this way, the Boolean expressions are given which we want to implement for simplification of any logic expressions. With the help of these Boolean expressions, we can minimize the logical expressions, and by default, we are going to minimize the logic diagrams of the digital circuits. Here we have to learn again the De Morgan's theorem. Basically, there are two statements for De Morgan's theorem. The first statement indicates the complement of the product of two variables is equal to the sum of complements of individual variables. That is, we are assuming here the two variables a, b, and the complement for that is equal to a complement plus b complements. Here we observe the table, and the table contains the variable which are expressed in your statement 1. That is, a is the variable, b is the variable, a complement, b complement, a into b complement of the products, and a bar plus b bar, that is a complement of a bar plus b bar. In short, we want to show a b complement is equal to a complement plus b complement. That is, left hand side is equal to right hand side. Second statement for De Morgan's indicate the complement of the sum of two variables is equal to the product of the complement of each variable. That indicates if two variables are a and b, then a plus b complement is equal to a complement into b complements. Here the table indicates the variables used, and if you are observing for the statement, that is left hand side is equal to right hand side in the table. This is nothing but a short or the brief introductions of your logic gates, the Boolean expressions, and the De Morgan's theorem. Thank you.